Welcome to the deep dive. We take fascinating source material and really extract the core insights for you.
Giving you the knowledge you need, basically, without all the overwhelm.
And today, we're tackling a really big one, intelligence.
Yeah, we're drawing from a pretty dense academic exploration of machine superintelligence. We'll be focusing quite a bit on what intelligence even is.
Exactly. Because you, our listener, you want to get this, understand it deeply, but, efficiently, see the different angles.
And hopefully have a few of those aha moments that make it all click.
Right. So this deep dive, it's designed for that. We'll navigate the complexities, hopefully give you a much clearer picture of this, well, pretty crucial concept.
You know, what's really striking right from the start of the source material is how many AI discussions just sort of gloss over the basics.
What is intelligence?
Exactly.
Okay.
They jump straight into these super complex algorithms, maybe give a quick nod to the Turing test, but often admit, a precise definition is kind of elusive.
Okay, yeah, let's unpack that. It feels a bit like trying to build the ultimate car without actually agreeing on what makes something a car in the first place.
Precisely. And our source really gets into this. It outlines broadly two main camps for how people have historically thought about intelligence.
Okay. Where are they?
So one view is that intelligence is fundamentally one single general ability. Think of Spearman's G factor.
G for general.
Right, general intelligence, this underlying thing that affects how well you do on all sorts of mental tasks. And within that view, you also have Cattell's idea of fluid versus crystallized intelligence.
Fluid being like raw problem-solving power.
Yeah, your ability to think flexibly, deal with new problems, and crystallized is more about the knowledge and skills you pick up over time.
So like raw horsepower versus the tools in your mental garage.
That's a good analogy. A young person might have high fluid intelligence, but an older, experienced person might have much more crystallized intelligence. It's a key distinction.
And that difference, one general ability versus maybe specific tools, that must have huge implications for AI, right? Are we aiming for one big breakthrough or lots of specialized skill?
Exactly. That's the core tension. Then the other side of the coin.
Is that intelligence isn't one thing?
Right. It's seen as a collection of distinct abilities. You've got Thurstone, who identified, I think, 7 primary mental abilities, things like verbal comprehension, spatial visualization.
Okay.
Sternberg, in an older model, talked about analytical, creative, and practical intelligence. And then there's Guilford's structure of intellect, which got incredibly detailed, like 150 different categories based on content, operation, product.
Whoa, 150. That sounds unwieldy.
It did face criticism about, how practical it was to actually measure all that. But then you have Howard Gardner's multiple intelligences, which is probably more familiar to people.
Yeah, linguistic, musical, logical, mathematical, spatial, that sort of thing.
Exactly. The idea there is that these are distinct enough that they should be considered separate types of intelligence.
But how does that square with the G-factor idea? Because often, people who are good at one thing seem pretty good at others, too.
That's a really important point. And the source mentions this. While Gardner's theory is popular, its scientific standing is debated. And crucially, even with these multiple intelligences, studies often find positive correlations between performance in these different areas.
Ah, so it sort of loops back towards Spearman's G maybe influencing these other abilities.
Kind of, yeah. Suggesting maybe a hierarchical structure, a general factor influencing more specific skills. That hierarchical view is actually pretty common now.
Okay, so with all these different viewpoints flying around, does our source actually land on a preferred definition?
It highlights one by Gottfredson, which is pretty comprehensive. Let me see. A very general mental capability that, among other things, involves the ability to reason, plan, solve problems, think abstractly, comprehend complex ideas, learn quickly, and learn from experience.
Okay, that sounds pretty solid. It covers a lot of what you'd intuitively call intelligence.
It does, but the source also contrasts this with a slightly different angle, more abstract, maybe more performance-based.
How so?
Well, instead of defining intelligence by a specific set of internal abilities, it looks at the effect of those abilities. The idea is that intelligent behavior could come from different combinations of capacities, maybe some very unlike human ones.
Right, so focus on the outcome, not necessarily how you got there. That's actually a really key difference, especially for AI.
It is. What else? Yes. Other definitions focus on achieving goals, adapting to new situations, or just performing well on tests or tasks, like Draver's definition.
Hmm.
Then you have definitions emphasizing abstract thinking, like termins. And one I found particularly interesting was from Woodrow, the capacity to acquire capacity.
The capacity to acquire capacities. So learning how to learn, almost.
Kind of. It shifts the focus from what you know right now to your ability to learn and develop new skills. Which brings up that debate again.
Hmm.
Is the fast learner inherently more intelligent than the person who already knows a lot?
Yeah, that echoes the fluid versus crystallized thing again. Potential versus current knowledge. Were there any definitions the source thought were, well, less useful?
Yeah, it flags definitions that basically just swap one fuzzy term for another, like Henman defining intelligence as the capacity for knowledge and knowledge possessed.
Okay, but then you have to define knowledge.
Exactly. What counts as knowledge versus just data? The source jokes that by that definition, a library or even the internet could be called intelligent.
Huh. Okay, point taken. So once we have some ideas about what intelligence might be, the next hurdle is measuring it. Intelligence tests.
Absolutely. And the source stresses two vital things for any good test: reliability and validity.
Reliability meaning you get consistent results if you repeat the test.
Yeah. And validity meaning the test actually measures what it claims to measure intelligence in this case.
And a key part of validity is predictive power, right? Like, does it predict how well someone will do in school?
Exactly. That's a big one. A valid test should have some predictive power for relevant outcomes.
Now, we mostly think of standard IQ tests, but the source mentioned different types of tests.
Uh-huh. It makes a distinction between static tests and dynamic tests.
Static being the usual kind, one-shot problem solving.
Pretty much. Testing your current knowledge, how you solve a problem right then and there. Dynamic tests are different. They focus more on your ability to learn and adapt.
How do they work?
Well, typically you interact with the tester. They give you feedback after you try a problem, and then you get a chance to adjust your strategy for the next one. It's measuring learning potential more directly.
That sounds much more, well, dynamic. Less passive than just filling in bubbles. So how do these tests develop historically?
Our source traces it back to the Binet-Simon scale, early days. But that was heavily focused on verbal skills.
Which could be a problem for some people, right?
Definitely. Think about people who were deaf or didn't speak the test language fluently. So Wechsler came along and developed tests incorporating nonverbal tasks alongside the verbal ones.
Ah, like the Waze test. Wechsler Adult Intelligence Scale.
Exactly. Those became, and still are, widely used standards. Modern versions, both the Wechsler scales and the Stanford Binet, assess a pretty broad range of things. Now, fluid reasoning, knowledge, quantitative stuff, visual spatial processing, working memory.
Okay, and then there's Raven's progressive matrices. I remember hearing that was designed to be more culture fair.
That was the goal, yeah. Raven tried to minimize cultural bias by using abstract visual patterns, sequences of shapes.
You have to figure out the pattern and pick the next shape.
Precisely. And the source notes these are considered very geloaded.
Meaning they tap heavily into that general intelligence factor.
Yes, because they require fundamental abstract reasoning. And interestingly, the ability to apply Occam's razor, preferring the simplest pattern or rule that fits the sequence, you're not just seeing shapes, you're evaluating the complexity of potential underlying rules.
Fascinating. Okay, so how does all this translate to measuring intelligence in machines, in AI?
Well, that leads to this idea of psychometric AI, basically trying to evaluate AI systems using tests originally designed for humans.
But I can see problems there.
Oh, yeah. The source points them out. Like, what's the right scope? Which human tests should an AI take? And the big one, couldn't an AI just be trained specifically to ace those tests without having real general intelligence?
Right, it could become a champion test taker for those specific tests, but maybe useless at anything else.
Exactly. So the source introduces another approach called the C-test. This tries to measure intelligence more formally, using ideas from complexity theory.
Complexity theory, how does that work?
The basic idea is that harder problems require more intelligence. The C-test uses sequence prediction problems, like Raven's, but the difficulty is explicitly linked to something called Kolmogorov complexity.
Kolmogorov complexity, remind me.
In simple terms, it's a measure of the shortest possible computer program needed to generate that sequence or data. Shorter program means simpler, less complex.
Ah, okay. So the C-test gives problems with known complexity levels.
Yes. And interestingly, studies apparently show a positive correlation between human scores on the C-test and their scores on traditional IQ tests.
So it's trying to measure the inherent complexity an intelligence can handle, rather than just performance on specific tasks.
Yeah.
Quite a different angle.
It is. The source gives examples like ADGJA having a complexity of 9 answer M, or a trickier one, CABD complexity 14 answer D.
Okay, so we've got different definitions, different ways to measure. Now the source really dives into the theory behind intelligent machines, right? Universal artificial intelligence.
Yeah, this is where it gets quite theoretical, focusing heavily on Hutter's AIXI agent. It's presented as this mathematically optimal model for an agent that can learn to act effectively in pretty much any computable environment it finds itself in.
Wow, okay, and it starts with inductive inference.
Right. Inductive inference is just that process of looking at observations and trying to figure out the underlying patterns or causes. It's fundamental to science, business, everyday life.
Like figuring out why the coffee machine breaks down every Monday.
Exactly. Or, more formally, taking data and picking the most likely hypothesis to explain it, usually so you can predict what happens next.
And the sequence example, 1, 3, 5, 7.
Perfect illustration. We see that, we immediately think, odd numbers predict 9.
But you could make a super complicated formula that also fits 1, 3, 5, 7, but predicts, I don't know, 42 next.
You could. Which brings us back to Occam's razor. We instinctively prefer the simplest explanation that fits the data. It's usually the better bet.
And the source mentioned earlier that even standard IQ tests kind of measure this implicitly. How do we make this preference for simplicity more formal, more mathematical?
Well, one way is through Bayesian inference. Using Bayes' rule lets you update your belief in different hypotheses as you get more data, factoring in your prior assumptions.
Okay, but the tricky part is those prior assumptions, right?
Yeah.
How likely you thought each hypothesis was before seeing data.
That's a huge challenge. The source mentions the indifference principle. Maybe assume all possibilities are equally likely to start. That breaks down mathematically if you have infinite possibilities.
Right? You can't assign equal probability to an infinite number of things. So what's the alternative?
The source suggests focusing on predicting binary sequences of zeros and ones. It turns out to be a more robust way to handle computability. You assume there's some unknown program or process generating the zeros and ones, and you want to predict the next bit.
And that leads to Solomonov's prior. Sounds important.
It's considered foundational in this area. Solomonov's prior defines the probability of seeing a particular sequence based on the chance that a randomly generated program running on a universal Turing machine would output that sequence.
Randomly generated program.
Yeah.
Meaning just random zeros and ones making up the code.
Pretty much. Each bit of the program code has a 50-50 chance.
Okay, so, wait. Shorter programs are more likely to be generated randomly just by chance, right?
Exactly.
So if a short program happens to produce my sequence, that sequence gets a higher prior probability.
You got it. And this connects directly to Kolmogorov complexity, the length of the shortest program that generates the sequence. Simpler sequences, those with low Kolmogorov complexity, get higher prior probability. It's Occam's razor formalized mathematically.
Wow. It's like the math itself prefers simplicity. That's kind of elegant.
It really is. Now, the source distinguishes between passive and active learning.
Okay, what's the difference?
Passive learning, like in basic Solomonoff induction, is just observing and predicting. Your predictions don't change what you're observing, like predicting planet movements.
My prediction doesn't make Mars change course, hopefully.
Right, but in active learning, the agent takes actions that do affect the environment and what it observes next.
Like playing chess. My move changes the board, changes what my opponent does.
Exactly. And this is where Hutter's AIXI agent comes in. It's designed as an active agent.
So it learns by doing, by interacting.
Yes. It uses a kind of universal prior over possible active environments, again based on the Kolmogorov complexity of describing those environments. It tries to maximize future rewards by learning how the environment works through interaction.
But the source has that heaven and hell example.
Yeah.
That shows a limitation, doesn't it?
It does. It highlights a crucial point. Imagine AIXI faces two doors. Behind one is infinite reward, heaven. Behind the other, nothing, hell. It has no prior information. It has to pick one.
And once it picks, it's stuck.
Right. An agent that knew the setup could always pick heaven. But a general agent, starting from scratch, can't know everything. It has to make the best guess based on its principles, like Occam's razor, even if the guess turns out wrong in that specific case.
So perfect performance in every possible situation is impossible. What's the goal, then, for a universal agent like AIXL?
The source introduces Pareto optimality.
Pareto optimality.
Yeah.
Like in economics.
Similar idea. An agent is Pareto optimal if there's no other agent that does strictly better in all possible environments and definitely better in at least one. AI Psycho might not be the absolute best in some specific weird environment, but no other single agent consistently beats it everywhere.
Okay, so it's about being robustly good across the board, not necessarily perfect in every niche.
Exactly. That's a much more realistic benchmark. The source states AIXI is Pareto optimal in this sense.
And then it talks about self-optimizing agents
Yeah.
in specific kinds of environments.
Yeah, things like ergodic Markov decision processes or MDPs. These are environments where basically the long-term statistics are stable. An agent interacting repeatedly can eventually learn the optimal way to behave.
Okay, so environments with some predictability.
Right. The source briefly mentions different classes,
Yeah.
passive ones like Markov chains, where the next state depends only on the current state, bandits, where the environment reacts just to your last action, and MDPs, where the next state depends on both the current state and your action. Many of these, it argues, can be modeled as or reduced to ergodic MDPs.
So understanding these environment types helps understand how a general intelligence might learn in different worlds it could encounter.
Precisely. Okay, so now we have this powerful theoretical model, universal AI. The source then asks, can we actually use this theory to formally define intelligence itself?
Instead of just describing an intelligent agent, define the property.
Exactly. It mentions something called the intelligence-order relation, a mathematical way to compare agents. The key idea is shifting away from just performance on narrow tasks.
Towards adaptability.
Yes. Real intelligence, the argument goes, is about performing well across a wide range of different environments and complexities. That's the flexibility humans have, which most current specialized AI lacks.
And Occam's razor pops up again here, as part of intelligent behavior.
Absolutely. Preferring simpler explanations is seen as core to rational, intelligent action. The source uses a dumb luck game example.
How does that work?
Imagine a situation where, based on all past evidence and the principle of simplicity, one action seems clearly the most intelligent. But due to some hidden complex factor you couldn't know about, that action leads to a bad outcome.
So you made the smart choice but got unlucky.
Exactly. The point is, the choice itself was intelligent because it followed rational principles based on available information. Intelligence isn't synonymous with guaranteed success in every single instance.
Okay, that makes sense. So when evaluating this universal intelligence, how do we factor that in?
The idea is to weight the environments not just by how hard they are, but by their Kolmogorov complexity. Simpler environments, being more probable under the Solomonov prior, should carry more weight in the overall assessment. An intelligent agent should handle a broad spectrum, but mastery of simpler, more likely worlds counts for more.
Right. Now, trying to pin down intelligence with math equations, I imagine that gets some pushback. What criticisms does the source mention?
Oh, yeah. One is it's obvious critique that this is just fancy reinforcement learning. The source counters that by pointing to the unique combination of RL, Occam's razor, and complexity theory and the attempt to formally link it to intuitive definitions.
What else?
There's Bloch's blockhead argument.
Ah, the giant lookup table idea. Something that could pass the Turing test by having a pre-programmed answer for every possible conversation, but without any real understanding.
That's the one. The source acknowledges this, saying its approach is functional. It focuses on performance across many environments, not the internal understanding. And finally, the no free lunch theorem.
Which says no single algorithm is best for all possible problems.
Right. But the source argues it doesn't apply here because we're not assuming all environments problems are equally likely. The Solomonov prior, based on complexity, gives a non-uniform distribution. Simpler environments are inherently more probable.
Okay, so the theoretical preference for simplicity sidesteps the no free lunch issue. Got it.
Right.
So we have the theory. Does it actually tell us if creating super intelligent machines is, possible in practice?
The source moves on to that, yeah. First, it tries to knock down some common myths, like machines only being logical or only doing exactly what they're programmed for.
Which isn't really true anymore, is it? We see AI finding creative solutions in games, for example.
Exactly. AI has surprised us plenty of times already, finding novel strategies, exceeding human performance in complex domains like Go or protein folding.
What about the argument that there's something sort of special or mysterious about human consciousness that machines just can't replicate?
The source frames that as a kind of vitalism invoking something non-physical to explain biology or consciousness. It suggests science tends to eventually find physical explanations for complex phenomena.
It uses the meat machine analogy.
Yeah, basically saying the brain is a machine, albeit a biological one made of meat. And biological machines might have limitations, size, energy use, signal speed that artificial systems could potentially overcome. Silicon can be faster, bigger, maybe more efficient than neurons eventually.
Okay, so if it's theoretically plausible, what are the potential routes to actually building these things?
The source lays out a few main paths.
Yeah.
One is trying to scale up the theories we just discussed, like AIXI, huge potential power, but the computational cost is astronomical right now. Maybe approximations could work, like MCAIX CTW.
So powerful idea, hard to build. What else?
Brain simulation, trying to replicate the human brain or key parts like the neocortex in software.
That sounds incredibly difficult.
Immensely. You need to observe the brain in enough detail, understand how it's all wired and how it works. It's a massive challenge. But there's hope, focusing maybe on the neocortex, which seems to have a somewhat uniform structure, suggesting a potentially general learning algorithm is at play there. There are big projects working on this, estimating the huge computational power needed.
Okay, so scaling theory, simulating brains, any other paths?
Artificial evolution. Basically, using principles of natural selection to evolve complex programs or neural networks over generations.
Letting the computer figure it out through trial and error on a massive scale?
Sort of. Challenges there include keeping enough diversity in the evolving population and figuring out how to properly measure the fitness of complex evolving agents. But there are ideas for tackling those issues too.
So multiple potential avenues, none guaranteed, all incredibly hard, but maybe not impossible.
That seems to be the takeaway. The timeline is anyone's guess, but the source argues it's not obvious why it should fail eventually.
And the final section just touches on the implications if we do succeed.
Right. Briefly acknowledging the enormous potential upside, solving major world problems, unprecedented wealth, but also the potential downsides, the nightmare scenarios people worry about.
And it notes that serious discussion of this, especially the safety aspects, is relatively recent but growing.
Yeah, historically maybe not enough academic focus, but now you have dedicated organizations like AORI, formerly SIAI, and thinkers like Nick Bostrom, Bill Joy, Ray Kurzweil really pushing these conversations about safety and ethics into the mainstream.
Okay, wow, that was a lot to cover. So, to quickly recap this deep dive, we looked at how hard it is just to define intelligence is a one thing, many things, potential, performance.
Right. Then how we try to measure it, from traditional static IQ tests to dynamic tests focusing on learning, and more abstract ideas like Raven's matrices and the complexity-based C-test.
Then we plunged into the deep end of theory with universal AI, Solomonov's prior, Kolmogorov complexity, AI, XI, formalizing Occam's razor.
Distinguishing passive observation from active learning, understanding limitations like the heaven-hell problem, but also concepts like Pareto optimality for general agents.
We saw how that theory could even be used to define intelligence based on adaptability and complexity, and address some key criticisms of that approach.
And finally, we considered the practical possibility paths like scaling theory, brain simulation, evolution, and the immense, almost unimaginable implications if superintelligence is achieved.
And hopefully you, listening, feel like you've got a much better handle on these ideas now. It's definitely a field moving fast, lots of unknowns, but these frameworks give us tools to think about it.
Definitely. So, maybe a final thought for you to chew on. Given everything we've discussed, the potential power, the uncertainty, what do you think are the most critical questions humanity should be asking itself right now about this path?
Or maybe, thinking back to all those definitions, which aspect of intelligence, raw learning speed, accumulated knowledge, adaptability, abstract reasoning do you think is the most vital ingredient we need to get right for future AI?
Lots to ponder there.
Indeed. We hope this deep dive gave you some valuable insights and maybe spark some new questions.
Thanks for joining us.